There are four states of matter we tend to observe in everyday life. We have solids, liquids, gases, and plasmas. But for our study of fundamental physics, we're just going to focus on the first three, at least for now. So gases and liquids come under the category of fluids. And a fluid is a non-solid state of matter in which the atoms or molecules are free to move past each other. And we can see this up in the animations up here. These balls represent the atoms or molecules of a certain substance. And with the liquids and the gases, these molecules are free to move around. With the solids, however, these atoms are fixed in place and they're not free to move or migrate. When the atoms or molecules are free to move around, the matter is able to flow and to change its shape in the process. And all fluids exhibit this property. So for example, when you pour orange juice from a square container into a cylindrical glass, the juice is able to flow out of the container into the cup and change its shape in the process. Solid objects, on the other hand, are not able to flow and change their shape, at least not easily, and therefore not considered to be fluids. And if you have a look at the animation here, the reason why solids don't flow under normal temperatures and pressures makes a lot more sense, because the atoms are locked in place. They cannot flow. So solids have a definite shape, while fluids do not have a definite shape. Even though gases and liquids are fluids, liquids are also very difficult to compress, much like solids. And therefore, liquids don't change their volume easily under pressure. But gases, on the other hand, can be compressed quite easily. So before we talk about buoyancy, we need to define mass density. Buoyancy occurs in all fluids, but the mass density of the fluid and the mass density of the object immersed in the fluid plays an important role in the buoyancy of the object. So if we have our fluid here, and let's imagine our fluid is water. If we immerse some plywood in this water, the plywood is less dense than the surrounding water, and therefore its buoyancy force will have a greater value than the plywood's weight. And these are vectors. So if this buoyancy force is greater than the plywood's weight, then the vector sum of these forces will point upwards. So the net force will be in this direction, which means that the plywood would float to the surface. If this object here was a piece of iron, iron is a lot more dense than the surrounding water. And therefore, its buoyancy would be low compared to the mass of the bar. But there's still a buoyancy force. So what is mass density? When we talk about the mass density of any object, we're really talking about how much mass there is per unit volume. Or in other words, how much matter is contained in some volume of space. The more matter you can pack in a fixed volume, the higher the density will be. So imagine this container, or this box here, contains gas molecules. And this container here contains the same gas, but at a higher density. You can see here that we're packing in more gas molecules per unit volume in this container than in this container, which means that this container has a low mass density compared to this container. So mass density is often represented by the Greek letter rho and is equal to the mass of a solid or fluid divided by the volume this mass occupies. So mass divided by volume. And the SI unit of mass density is kilograms per meter cubed. So let's look at a couple of examples of densities from various materials. And I've written them here from highest to lowest density. So we have a variety of substances here. We've got gold at the top with a density of 19,300 kilograms per meter cubed. Then we've got mercury at 13,600, then iron, fresh water, ice, and then air. And these are the densities of these objects, of these substances, at 0 degrees Celsius and at 1 atmospheric pressure, except for fresh water here, which is at 4 degrees Celsius. Now, atmospheric pressure and temperature have a large impact on the density of gases. Unlike solids and liquids here, gases can be easily compressed. And we saw why this was from the gas animation that I showed you previously. When the surrounding atmospheric pressure is low, the gas molecules have more room to expand outwards, and therefore their density drops, like we can see here. So in other words, there's less amount of mass or molecules in a unit volume of space. So the same is true when we heat a gas that is not contained, but we'll get into this in a future lesson. So if we have a look back at our table of densities here, we have fresh water and ice. What do you notice about the densities of these two substances? We see that ice is slightly less dense than water. There is less mass per unit volume. Ice also floats on water, and this is because less dense objects float on more dense fluids due to the principle of buoyancy. And we'll cover this in more detail shortly when we talk about Archimedes' Principle. What about the second liquid in our table, the mercury? If we had a bar of gold and a bar of iron, which one will float and which one will sink in a container of mercury? So because gold is more dense than the mercury, it will sink beneath the surface. The iron bar has a lower density than mercury, so it will float on the mercury surface. Now all fluids exert an upward force on objects that are either partially or completely submerged within the fluid. So this object is completely submerged within this fluid here, and this object is only partially submerged. But both objects here have an upward buoyant force. Now there's always an upward buoyant force, no matter whether the object sinks, stays stationary where it is, or whether it's floating upwards or resting on the surface. There's always a buoyant force if an object is partially submerged or fully submerged in a fluid. And in fact, there's a very small buoyant force on you now that is acting against the force of gravity. And the reason we're experiencing this buoyancy force is because we're submerged within a fluid. Because if you remember back to our original definition at the beginning of the video, air is a gas, and a gas is also a fluid because it flows. This buoyancy force, though, compared to your weight, which is measured by your mass multiplied by the acceleration due to gravity, is very small compared to your weight. So this upward force acting on you is not large enough to lift you off the ground, because your body's density is far greater than the density of the fluid that you're in, the air. But because all objects have this buoyancy force within a fluid, and these forces are vectors here, they have a magnitude and a direction, the net force on the object is simply the vector sum of these two vectors here. So the net force on any object in a fluid is equal to the buoyancy force, Fb, and we're going to say that the upward direction is positive and the downward direction is negative in terms of vectors, minus your weight, or the object's weight. So if we have a look at these three examples here, from this vector sum here, we can see what the net force is on each of these objects and which direction they would accelerate within this fluid. So because the buoyancy force on this object is smaller than its weight, then we've got an overall negative F net. And due to our convention here, a negative force vector points downwards. So we got an F net pointing downwards, meaning that our object will accelerate down in this situation. The same is true for any objects within an atmosphere. So long as the object is denser than the surrounding air, the buoyancy force is going to be lower than the weight. And therefore, the net force will point in the negative direction. What about this example here? In this example, the object is neither accelerating downwards and it's not accelerating upwards. The buoyancy force has the same magnitude as the weight of the object. These two arrows here are the same length. So when we have a buoyancy force and the weight being exactly the same, they sum to zero. So the net force here is zero. So if we take this object here that's within water, for example, because the F net is slightly lower than the object's weight, it will feel lighter underwater. Now the F net force is also called the apparent weight. And it's the weight of an object immersed within a fluid after we've performed this vector sum here. So let's expand on this a bit and look at three objects that are immersed in water. Object 1 is more dense than the surrounding water. Object 2 has the same density as the surrounding water. And Object 3 has a lower density than the surrounding water. And all three of these objects here have an equal mass and therefore an equal weight. Even though they're different sizes here, they have different volumes, their mass in kilograms is exactly the same. And you can see here that their weight vector is the same length. Now remember, the true weight of an object is the mass of the object multiplied by the gravitational acceleration, mg. But each of these objects here has a different buoyant force. The net force on each object is simply the sum, the vector sum, of the buoyant force and the weight of the object, which we talked about earlier. F net is equal to the buoyancy minus the weight of the object. And that's the positive direction, and that's the negative direction. And remember, F net is the apparent weight of the object within the fluid. So if you were to rank the apparent weight of all these three objects here, what order would you rank them from highest apparent weight to lowest apparent weight? And can you tell me which direction each of these objects are currently moving in within this water here? Now, Object 1 has the largest apparent weight because the buoyancy force here is relatively small compared to the actual object's weight. So if you're underwater and you're trying to lift this object up from the surface of a swimming pool, for example, it'll be a lot harder to lift this object up than these two objects. Object 2 has an apparent weight of 0 Because the buoyancy force is equal to the weight of the object. This object would remain stationary underwater. Object 3 has a negative apparent weight. Now, even though F net here will give you a positive value because the buoyancy force is greater than the weight of the object, the apparent weight would be negative because it would be floating up to the surface. And you would, in fact, have to hold it down if you didn't want it to float up towards the surface. So how do we find the magnitude of this buoyant force in the first place? How can we calculate this value? Well, to find the magnitude of the buoyant force acting on an object within a fluid, we use a rule known as Archimedes Principle, and we can state this as follows. So any object completely or partially submerged in a fluid experiences an upward buoyant force equal in magnitude to the weight of the fluid displaced by the object. So if we go back to our three objects, object 1 has the smallest volume, then object 2, and then object 3 has the largest volume here. Now remember, the weight of each object is exactly the same, but you can see that object 3 has displaced a lot more water than object 1. Effectively, these objects are pushing water out of the volume that they occupy. So again, the buoyant force is equal in magnitude to the weight of the fluid displaced by the object. Object 3 is displacing a lot more fluid, a lot more water than object 1. And so the buoyancy force is equal to the weight of the water that would be within this volume if the object wasn't there. And that's why object 3 has a larger buoyancy force. So let's put some numbers into this. So we're going to take object 1, we're going to give it some dimensions, and we're going to work out what this buoyancy force is on this object. So it has a width of 0.1 meters, a depth of 0.05 meters, and a height of 0.02 meters. We get a volume of 1.00 times 10 to the minus 4 meters cubed. So that's our volume of our object 1. So according to Archimedes' principle up here, the upward buoyant force is equal in magnitude to the weight of the water that is displaced. So the amount of water displaced is equal to the volume here. So what is the weight of this amount of water here? How can we work this out? Well, the density of water, of fresh water at 4 degrees Celsius, if we go back to our table up here, is 1,000 kilograms per meter cubed. And remember, mass density is calculated like this. Rho is equal to the mass divided by the volume. We've already got the volume up here. We've got the density of the surrounding water, but we don't have the mass yet. So we need to rearrange this equation. The mass is equal to the density multiplied by the volume. So the mass of this displaced water here is equal to 1.00 times 10 to the power of 3 kilograms per meter cubed multiplied by the volume. 1.00 times 10 to the minus 4 meters cubed. And you can see here that the meters cubed, the volume here cancels out the units, leaving us with kilograms. So the mass of this water would equal 0.100 kilograms, or about 100 grams. But remember, we need to find the weight of this water, because the weight of this volume of water is going to be equal to the buoyancy force. And we find out the weight of any object with the mass of the object multiplied by the gravitational acceleration. So we've got 0.100 kilograms for the weight of our water, for the mass of our water, multiplied by 9.81 meters per second squared, which is the acceleration due to gravity at the Earth's surface. And we get a value of 0.981 newtons. And due to Archimedes' principle, the buoyant force is equal in magnitude to the weight of the fluid displaced. And this is the weight of the fluid displaced, FB. So the buoyant force is equal to 0.981 newtons for any object of this volume submerged in water, fresh water. So we got the buoyancy force. But what is the weight of this object? Well, it depends on what the object is made of. Let's say this bar here is a piece of solid gold. And gold, from our density table up here, has a density of 19,300 kilograms per meter cubed. So now we can work out the true weight of this object. Again, with the mass density formula, rho is equal to the mass divided by the volume. We've already worked out the volume here. We know the density of gold, which is, I think, 19.3 times 10 to the power of 3 kilograms per meter cubed. We need to find the mass again of this amount of gold. So the mass is equal to the density multiplied by the volume, which is equal to 19.3 times 10 to the power 3 kilograms per meter cubed, multiplied by 1.00 times 10 to the minus 4 meters cubed. So the mass is 1.93 kilograms. And the weight of this gold is equal to 1.93 kilograms multiplied by the gravitational acceleration of 9.81 meters per second squared. We get a value of 18.9 newtons. So 18.9 newtons is the true weight of this object. But because this gold is fully submerged within water, it's going to feel slightly lighter than it would do in air. And it will feel slightly lighter by about 1 newton. So the net force on this gold object here will be equal to the buoyancy force, 0.981 newtons, minus the weight of the object, 18.9 newtons. So the net force acting on this object is negative 17.9 newtons to 3 significant figures. And this negative sign here indicates that the net force is pointing down, which means that the object is going to sink. So whether an object floats or sinks depends on this net force here. A net force of 0 would mean that it would be stationary underwater, it wouldn't float or sink. A negative net force will mean it will sink, and if it was positive, it will float upwards. So the buoyancy force depends on the density of the object compared to the fluid that surrounds it. So now we know that the buoyancy force is simply the mass of the displaced fluid multiplied by the gravitational acceleration. So we can rewrite this equation here. So the mass of the displaced fluid multiplied by g, and the weight of the object can be rewritten as the mass of the object multiplied by the gravitational acceleration. And if you remember earlier, we rearranged the mass density equation, mass over volume, to make the mass the subject of the equation. So the mass is equal to the density of the object multiplied by its volume. We've just rearranged this. And therefore, we can replace the mass terms here with this term. So now the F net force is equal to the density of the surrounding fluid multiplied by the volume of the fluid that was displaced by the object multiplied by the gravitational acceleration minus the density of the actual object within the fluid multiplied by the volume of the object in the fluid multiplied by the gravitational acceleration. We can simplify this further by taking the gravitational acceleration outside the brackets here. And if this object is fully submerged, it's not floating on the surface, then these two volume terms here, the volume of the fluid that is displaced and the volume of the object itself, are equal to one another. So the volume of the object will be equal to the volume of the fluid displaced. So we can simplify this further and bring the volume outside of the brackets here. So the density of the fluid minus the density of the object multiplied by the volume that is displaced by the object multiplied by the gravitational acceleration. So the F net force can be determined simply by the difference in the density of the surrounding fluid and the density of the object. If the density of the object is higher than the density of the fluid, then we will get a negative value for the F net. And a negative F net value points in the downward direction. It doesn't matter what the volume of the object is. It doesn't matter what the acceleration due to gravity is. The direction that the object will move only matters on the difference in the density from the object and the surrounding fluid. So we can actually develop a really useful expression by considering the ratios of the weight of an object and the buoyant force of a fully submerged object. So if we got the weight of an object, and that's equal to the density of the object multiplied by the object's volume and the acceleration due to gravity. And if we divide this by the buoyancy force, and this is the buoyancy force term, the density of the fluid multiplied by the volume of the fluid displaced by the object and the acceleration due to gravity, we can cancel out these terms here. And we're left with this expression, where if we know three of these terms here, we can work out the fourth term. And we're going to use this expression now in the following problem. So imagine you've been sold a ring, and the person that sold it to you claims it's 100% gold. So you decide to go home and test this claim with the help of the expression above. So how can we use this expression above to find out whether this ring is 100% gold? So to get the weight of the object, we can simply weigh it using a scale and see what value we get. But because this ring is within air, which is also a fluid, we also have a very small buoyancy force acting on the ring while we're weighing it right here. But because this metal ring is so much denser than the surrounding air, this upward buoyancy force is going to be very small compared to the weight of the ring. So here we can ignore it for now. And the weight of the object can be worked out from this scale here. So if this scale says that this ring weighs 5 grams, so the mass of the ring is equal to 0.00500 kilograms. Its weight is equal to its mass, 0.00500 kilograms, multiplied by the acceleration due to gravity. We get a value of 0.0500 newtons. So we've already got our first term here, the weight of the ring. Next, we need to perform the same weight measurement, but now we fully submerge this ring in a fluid of known density, for example, water. So because this ring is within a slightly dense fluid, there's going to be a slight buoyancy force pushing the ring up. So the apparent weight of this ring is going to be lower than the actual weight of the ring. So the apparent weight is equal to the weight of the ring within the air minus this buoyancy force. And remember, this is not a vector calculation. We're simply saying here that because the ring is now within a denser fluid, the apparent weight of the ring is going to be lower than it was in air. And we're interested in the buoyancy force here. We've already got the weight of the ring in the air, 0.05 newtons. The apparent weight we can read from the scale here, and we can rearrange this equation to find the buoyancy force. So the buoyancy force is equal to the original weight of the ring minus the apparent weight. So let's say that the apparent weight that we get is 0.0438 newtons. The buoyancy, the magnitude of the buoyancy force acting up on this ring within water is equal to 0.0500 newtons minus the apparent weight, 0.0438 newtons. So we get a buoyancy force of 0.00625 newtons. So we've got these two values here. We already know the density of water at 4 degrees Celsius, which is equal to 1,000 kilograms per meter cubed. So we've got these three values. All we need to do now is rearrange this expression here to make this density, the density of the object, the subject of the equation. So let's do that. So the density of the ring is equal to the weight of the object divided by the buoyancy force of the object in water multiplied by the density of the water or the fluid. We get a density of, when we sum this up together, we get an overall density of 8.00 times 10 to the 3 kilograms per meter cubed. So what does this mean? This density is lower than the density of pure gold. In fact, the density is closer to that of iron. So our ring could be made of some gold mixed in with other metals like copper, or it could just be gold-plated iron or steel. So we've talked a lot about the buoyant force for objects fully submerged in a fluid. But what about floating objects? What is the buoyant force on objects that are currently floating on top of a liquid? So for example, this boat here. So in this situation, there are two forces acting on this object, so long as the object is stationary. We have the downward gravitational force, or the weight of the object, but we also have a buoyancy force as well. Now, what do you think the magnitude of this buoyancy force is? And we have talked about this earlier in the video. So because this boat is floating on the water, and the boat isn't accelerating upwards or downwards, the boat is in equilibrium. So the two forces, the buoyant force and the weight of the object, are balanced and are equal in magnitude to one another. And remember, the magnitude of the buoyancy force is also equal to the volume is also equal to the weight of the volume that is displaced by the object in the fluid.